Hey guys, today we're looking at 6.6's notes, which is all about solving both exponential and logarithmic equations. So I apologize for the background noise. They're working on some road construction here and it's a little loud, so if you hear some stuff, they're both trimming some trees and pulling up some asphalt, so it is what it is. Hopefully it's not too distracting for you. So we're looking at 4-box notes today. Again, like I said, we're solving exponential and logarithmic equations. We solved exponential equations back in Algebra 1 when we were dealing with exponentials in that class as well. So this first 2 boxes should look familiar to us. There's some slight differences with solving some more complex ones, but we'll go ahead and just jump right into it. So I've got just some definitions here in box number 1, what an exponential equation is, which just like it sounds, it's an equation that has an exponential in it. So that the exponent is where my variable is hosted. So where my variable happens in my problem is in the exponent. So it could just be an x value, it could be a whole expression where we have some more complex stuff in the variable. The variable is in the exponent, but that's what an exponential equation is. We've got a couple of different ways that we can handle this. One kind of elegant way is with our property of equality. So in this, it tells me that if I have 2 different things that are set equal to each other that have the same base, if their if their bases are the same and they're equal to each other, then their exponents have to be equal to each other. So like we have here in the definition, if b to the x power equals b to the y power, that means that x has to equal y since that base is the same. And what that looks like with some numbers, an example here, if we know that 3 to the x power equals 3 to the 5th power, that tells me that x has to equal 5. So one strategy that we can do for solving equations here in box number 2 is we're going to try and rewrite both sides of my equation with the same base. So here 100 and 10 are not the same base, but I can rewrite both of those as a base of 10. Because I can rewrite 100 as 10 squared, and that's still to the x power. And then over on the right side, my 1 over 10, well, that's 10 to the negative 1st power, still to the x minus 3. So now all I have to do here is just kind of do my power rule. My exponent being raised to another exponent power tells me I have to multiply those 2 things together. So this is 10 to the 2x power equals 10 to the negative x plus 3 power. And now we have 2 things that set equal to each other that have the same base. That tells me that those 2 exponents have to be equal. So I can just solve that new miniature equation with just my exponents. 2x has to equal negative x plus 3. So I add x on both sides. Oops, undo, there we go. Those cancel out, so 3x equals 3. I divide by 3 and I get that x has to equal 1 in this case. So that's one way of solving an exponential equation. One less elegant way is actually utilizing those the inverse properties of logarithms and exponentials that we looked at in 6.4, I think it was, maybe it was 6.5, because here there's no way that we can rewrite 7 as a 2 for the base. So like 2 to some exponent power is not 7, so I can't rewrite both sides of my equation here so they're going to have the same base. So how I have to handle this is utilizing the fact that I know my log base 2 is the inverse of an exponential with a base of 2. So what I'm going to have to do here, I'm going to rewrite first just below so I have some space to write with. So what I have to do is take the log of base, with respect to base 2, on both sides. If I do the log base 2 on both sides, on this left side, my log base 2 and my base of 2 cancel out, and I'm just left with x. But then I have to make sure I do that on the other side as well. So depending on how the answer has to be formatted, log base 2 of 7 could be the correct answer. If the textbook, they, or I specify that I want it as a decimal, we would have to make sure we evaluate log base 2 of 7. So if that was going to be the case, I would have to use my change of base rule that we learned back in 6.5. So this is the same thing as either ln or common log of 7 over common log of 2. On our calculator, we can do that. We should end up with 2.807 for log base 2 of 7. So either of those 2 would be fine. If they specifically say round your answer to the nearest thousandth, the 3 decimal places, that would be what we'd have to do. If it doesn't say so, you can just leave it as log base 2 of 7. Okay, Box 3 are logarithmic equations. Kind of the same idea here. Our logarithmic equations are just equations that involve logarithms of variables. So now specifically, again, those variables are inside the log. So we're evaluating the log with exponent or with variables inside. I still have numerical bases. I still have numbers as bases. It's just going to be the x value or the variable is going to be inside the log. So again, we have that nice elegant property of equality. If I have the log of the same base on both sides of my equations, then whatever they're evaluating has to be equal to each other. So log base b of x equals log base b of y, if and only if x is equal to y. Meaning if x is equal to y, then that is true. If log base b of x equals log base b of y, then x equals y is true. So again, an example here, if we have log base 2 of x equaling log base 2 of 7, that means x has to be 7 because they have the same log of the base. So here for number 3 in box 4, again, if we have log of the same base, which ln, remember that's log base e, if I have those two things equal to each other, that means that what's inside my log, in this case what's inside my parenthesis, has to be equal to each other because we have the log of the same base on both sides. So I'll just set up that miniature equation, the kind of the simpler one, a chapter 1, algebra 1 problem, 4x minus 7 equals x plus 5, and we'll go through and solve that. So I'm going to subtract x on both sides. That gives me 3x minus 7 equals 5. I add 7 on both sides. That gives me 3x equals 12. I divide by 3, and I get that, I'll write it over here. X has to be positive 4. Positive 4 for my x value. And you could check this. I mean, you plug 4 in here. Over on the right side, you get log ln of 9. On the left side, 4 times 4 is 16, minus 7 is 9. So the ln of 9 on both sides, that makes sense. Again, you could evaluate and just get a decimal. Whatever floats your boat and makes you happy, go for gold. All right, for this last one, for number 4 in box 4, another one where I don't have log of the same base on both sides. So I'm going to have to use those inverse rules of exponential and logarithms, meaning that in this case, since I have the log base 2 on the left side, I have to put that as an exponent on a base of 2. Because remember, exponentials and logarithms of the same base cancel each other out. So I have my base of 2 on both sides. That means over here, those cancel each other out. I have 5x minus 17 equals 2 to the third power. So then I just go through and evaluate. So I'm going to first evaluate 2 to the third power, which is 8. And now I can add 17 on both sides. That gives me 5x equals 25. I divide by 5 on both sides, and I get that x has to be positive 5. Again, you could go through and check your answer. If I plug 5 in there, 5 times 5 is 25, minus 17 is 8, log base 2 of 8 is positive 3, because 2 to the third power is 8. So we're good to go. That is all I have for you for today, and that is 6.6. Your homework is on the screen there, page 338, 6 through 16, and 22 through 20, or 32, just the evens. So basically 6 through 32 evens, skipping 18 and 20. So however you want to think about that. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. We'll see you soon.